Hi everyone, welcome to the next video in the series. We're going to be talking about solids of revolution. There'll be two videos. One will be on the disk method and the other will be on the washer method. And so you can see here the objectives for this video, and I just want you to know that the cartoon accurately depicts how I put together this video. So one of the hardest things for students to do is to picture a two-dimensional object revolved around an axis, making a three-dimensional object. And so on the next couple of screens, I have showed you, shown this rectangle along the x-axis, and then shown you again what this solid looks like. And there are places on the web that will have applets that actually show that in real time. This one is a circle, right? So if you take the circle around the y-axis, and notice how they depict how they revolve that around. They put a little thing, if it says y-axis, and this becomes a donut or a torus. And then you can see here a triangle revolved around becomes a cone. And then a sphere is just going to be a semicircle revolved around the x-axis. That's what this one looks like. It kind of looks like a half donut if you go this way, right? If you do this one, this is going to be like almost like a torus with a straight edge down here. It's interesting to see that something that is like a triangle, has corners, actually turns out to be circular in parts. And this, where this is just a part right here, shows that it's just all circular. Anyway, those are kind of interesting. So the first thing I'd like to do is to look at a three-dimensional object that's familiar. We're going to look at the volume of a cylinder. Now maybe back in geometry days you learned to find the volume of a cylinder by memorizing a formula. I want to take a slightly different approach, looking at it geometrically. Right? So we know that the cylinder has two bases. This is a base, and then it also has a base here. They're both circles. And we know that we could find the volume of a cylinder if we took the area of the base and multiplied that by the number of bases, or in other words, the height of the cylinder. Okay, simple enough. And that would be equal to the volume. Well, we know that the area of a base is pi times the radius squared. And so if we replace that here, we had pi times the radius squared times the height of the cylinder, and that was the volume. Now that's a regular figure, right? That is going to be, every cylinder looks like that, every cylinder. But we're looking in calculus with irregular shapes. So here's another way of thinking of this familiar object. Call the base, instead of a circle, we'll call it a disk. And you can spell it with a K or a C, it doesn't matter. And then we're going to take the sum of the disks, all the disks that there are, the sum of all of them, right? And that would be the volume. Now, this idea then would lend itself to an integral, right? We would take the area of the disk times the number of disks. And we could make it an infinite number of disks, right? It doesn't have to be a unit long. All the disks could be an infinite number. And that would fill up the area, fill up the volume, and this would give us the volume, right? So this idea of using disks is what we're going to be using on irregular figures. So here's our first example. It says find the volume of the region between the curve y equals square root of x and the x-axis from 0, x equals 0 to x equals 1, and then take that area and revolve it around the x-axis. All right, so the first thing that we need to do is we need to graph this. So I know that the square root of x looks like this. I have 0, 0, 1, 1, and then 4, 2. Okay, so that's my y equals square root of x. I have the x-axis. I also know I'm going to revolve it around the x-axis, so I'm going to go ahead and write that. And I want to go from x equals 0 to 1. Okay, so I'm looking at this area right here, and I want to revolve that around the x-axis. So it's going to look something like this. I'm going to make it a little bit bigger, right? Okay, so the radius, right, of here's my circular, right, because it's going all the way around. The radius is going to be different each time, right? Here's the x-axis. So it's going to be this sometimes, this sometimes, this sometimes. So to represent all the radii, the radius of all of them is going to be the square root of x. It's going to be this function right here that we use to graph it, right? And so what I want to do then is I want to find that region, right? The radius varies. And so I need to use the radius as this. So I know that the area is going to be found by taking pi times the radius squared times the number of disks, right? And the number of disks will be infinitely small. So as I integrate this, I'm going to integrate it from 0 to 1. Pi is a constant. It comes out. Square root of x squared, and then the number of disks will be dx, because I'm going to take in an infinite number of disks to make up this slice. Okay, so when I integrate this, right, the square root squared is just x, and so this will be pi x squared over 2 from 0 to 1, and then the volume of this will be pi over 2. So real quick, let's look at some notes on this and some in general. The volume of a solid is equal to the sum of the area of the disk times the height of the solid, right? So in notation, that would be the same thing as the sum from I equals 1 to n of pi times the radius of the object squared, and in our case, I can't get that to right, the radius is going to be of the disk. So when you revolve it all the way around, right, and then if you take that in integral notation, you're going to have the integral, right, pi times the integral from a to b of the radius of my object squared dx, and that's what we did before. And then just some notes. Rx, right, the radius, is the distance from the curve to the axis of revolution. Okay, so it was that from the top of the curve down to the x-axis. A diagram's the best way to see what's happening, and the radius must always be perpendicular to the axis of revolution. So here's the next example, and once again, we're still graphing, and we're still graphing parabolas and lines, and basically that's what it is. And then we're looking at the area of that region that we want to revolve, okay? So this one's a little bit different because we're not revolving around the axis, x or y axis, we're revolving about a line, y equals 1. So it's just a little bit different. So let's graph. We're going to, first of all, graph the parabola. So it's 2 minus x squared, so that means it comes all the way up to here at 2, and then it's upside down. So over 1, down 1, over 1, down 1, over 2, 4, and then it's symmetrical about the y. So I have something that looks like this, and then I have the line y equals 1. So this is y equals 1. And so here's my region, and I am revolving it around this, okay? Later on, when we do a washer method, we'll revolve this little piece around the x-axis, and you'll see it look more like a torus or like a washer, if you're not like a washer and dryer, but like bolts, nuts and bolts washer. Okay, and so that's what we're getting ready to do, and so it's going to look a lot like a kind of a almost a sphere, except it's a little wonkier than a sphere. All right, so what we want to do is we want to set this up, and we see that if we revolve this around the axis, it's going to require a disk. So what we're going to do is set up the disk. So to find the volume using the disk, we're going to set the volume equal to pi, because it's a circular disk, the integral of the curve, right, squared. And then since we are going around this axis this direction, we're using a dx. So what we want to do is start at the axis and go straight up to the curve. That's going to be our capital R. All right, so we're trying to find this area, and remember from area under the curve, we do axis minus, we do one function minus the other function. So we have 2 minus x squared, and then minus 1, the other function. All right, and so if we combine that together, 2 minus 1 is 1 minus x squared quantity squared. All right, now we can integrate this by hand, of course. Since we have 2 minus 1, we have that 1 minus x squared, we would have pi, I guess I'm still in red. I also need to go from negative 1 to 1, and I have 1 minus x squared dx. So if I integrate that, that's going to be x minus x to the third over 3 from negative 1 to 1, negative 1 to 1, times pi. So our answer will have pi in it. And so when I put that in there, and at this point I probably would go get a calculator. You can work them by hand, but it's quite tedious actually. I'm going to end up with, it will have pi in it, so it will be 16 fifteenths pi. Okay, so there's always a twist, is there not? All right, so far we've been looking at horizontal axis of revolution. And so far we've been looking at things like this, where we are revolving it around the x-axis. And so the radius of my disks, they're all going to be vertical. All right, so horizontal axis, vertical rectangle. But what if you switch it? What if you want to revolve it around the y-axis? Then you're going to have a vertical axis of revolution. So just like what we did with the area between, the disk method can be used to find it. Here's horizontal. Notice that this is all x, all with respect to x. But you can also do a vertical axis, all with respect to y. And that's what the next or last example will be about. All right, this last example is also number 8 in your assignment that you'll get in class. So if you've watched the video, you will have already done number 8, and you don't have to do it again on your assignment. The other thing that the book has for this problem is a graph. So they go ahead and they graph this. They put in 0 for x and get 4. They put in 4 for x and get 0. And then you can see it's kind of this circle area. So this right here is the graph, right? And they want to revolve this around the y-axis. So the thing to remember then is, and according to that is perpendicular. So this is my radius of a disk, right? If you think about what a disk would look like, if I can draw it, something like that, right? So it's going to look something like that. Each one of those are going to be a disk. Well, what is it? Well, it's this. Except that because we're going around the y-axis, our integral is going to end up with a dy. So my radius squared, right, with a pi here, this is going to need to be in terms of y. And this one is in terms of x. So we need to solve it. So I'm going to square both sides, and that's going to leave me 16 minus x squared. And then I'm going to subtract the 16. So y squared minus 16 equals negative x squared. I'm going to switch the signs on the other side to divide by negative 1. And then I'm going to take the square root. All right, so once again, we're going to take the principal root, because if I do that, I'm going to end up with plus or minus, but I'm taking the principal root. So x is going to be equal to the square root of 16 minus y squared, which is kind of interesting. Okay, so that, my friends, is going to be the radius. So I'm going to put the square root of 16 minus y squared, quantity squared, because it's pi r squared dy. That's how we're finding the volume of all those disks. And I want to go from 0 to 4. So I just want to do the solid, and that's this 0 to this 4, because it's on the y. It just happens to be the same on both. And so when I put that in my calculator, actually I worked it by hand, because I ended up with pi times, because the square root squared is just going to be what's underneath. So I had y to over 3 plus 16y from 0 to 4. And so I ended up with 128 over 3 times pi. Now, if you put that in your calculator, you're going to get some ugly decimal, and I'll let you do that if you want to. I just did it by hand. And so that's pretty close to exactly what we want to do with this. So keep training your mind to see it the opposite way. There's a lot of stuff that goes into this, but you're going to be able to get it. And I will see you. Hope you took good notes. I'll see you in class.